All right, it's time to start. So first offline participants, thank you for braving the weather. I do hope that you all live in Delft. If you live otherwise, you would have to spend kind of rest of evening in the city. There will be no trains starting 2 o'clock. I hope you remember that. Otherwise, leave the audience immediately. Good. So we still are in the lecture 1. And I will start with this. There will be 5 transparencies about this. You might remember that we understood that we don't know probability theory. So there's a couple of formulas for probability theory. Let me remind you. So if we have distribution of what? We have discrete events, we have time interval, and we compute distribution, observation of number of events per time interval. And it appears to be handy to make a Fourier transform of that to study characteristic function. It has nice properties. One can compute momenta, very handy from this characteristic function. But it's not that important property that it is independent for, it factorizes for independent events. If you look at the distribution, it does know it. But if you look at characteristic function, it does factorize. Good. Since events separated by large time intervals are independent, it means that log of this characteristic function is proportional to time. Good. We could compute not only cumulants, but we could also do elementary event analysis. That was an attempt to do it for birds, well, because it's statistics, it's not only about physics, it is about any natural phenomenon, which you can express in numbers. And we notice if we, okay, so it's log, it's proportional to time of observation, it's log here, and here we expand in terms of this function. Right, and the coefficients will give us something about behavior goods, probability for a bird to be single, or to be a part of a couple, or to be a part of a big flock. All right, that's the use of it. Let us talk about electrons. I want you to understand and remember 2 limits, perhaps even without characteristic function, but it's important to recognize that there are 2 limits in quantum transport. First limit, if we consider tunnel junctions. Tunnel junctions means that transmission coefficients in all channels are small. What does it mean? Transmissions occur rarely, are separated by big intervals of time. And as such, they can be regarded as independent events. Very convenient. All right, and this is characteristic function for independent events. So its log eventually contains only this first power of this factor. Fine. Then there's something which people kind of could not recognize for a long time, although it is simple. Let us consider ideal transmission, right? And let us recall that electrons are quantum mechanical particles. And if there is no reflection, They just plane waves. They're plane waves, and as such, recall quantum mechanics, they have definite velocity, definite k vector. If they have definite k vector, definite velocity, it means that the current due to these electrons just does not fluctuate, right? And the current is just proportional to the average current, no fluctuations, and characteristic function is such. All right, perhaps without experience you don't get much use of these expressions, but that two limits you can get. Independent events for low transmission and the kind of very uninterruptible flow of current for ideal transmission. Very good. Now I'm ready to show you one formula called Levitov formula, which is generalization of Lambda formula. Lambda formula gives you average current. Levitov formula gives you statistics of electron transfers. As such, it is for characteristic function. Okay, its log is proportional to time interval. That's okay. Now we recall that it factorizes for independent events, so that each term in the sum presents independent events. Right, let us analyze this. First, integration over energy. What does it mean? It means that electron processes at different energies are independent. All right, that's logical. It is sum over channels, which means that electrons in different channels just don't know about each other, okay? That one can also accept. What is a little bit more difficult to accept? Oops. Jesus Christ, sorry. What is a little bit more difficult to accept, that electrons coming from the left and coming from the right are not independent. Somehow they know about each other. It is very difficult to accept if you kind of believe in locality and if you regard electrons as independent particles. Then what comes from the left that should not know about something which happens on the right. Good. If you attended my course of advanced quantum mechanics, I mentioned yesterday about this. In fact, the fact that electrons are fermions breaks this principle. Electrons are all quanta of electronic field. That's why electrons on the left and on the right, they know each other. Okay, that looks a bit abstract. Let me explain it in a simpler and still adequate language. I will talk about blocking factors. You also see them here. Okay, here and here. All right, these for electrons coming from the left. All right, it's proportional to filling factor because there has to be some electrons coming. But it's also multiplied by 1 minus Fr. What is this? What does it mean? Electron coming from the left should find an empty place on the right. Otherwise, it would not give. Right? And this is probability to find an empty place on the right. Same here, it comes from the right. It has to find an empty place on the left. Good. It is those are blocking factors, those are manifestations of statistics. And let me stress a simple but important conclusion. Let me draw perhaps energy diagram. So there will be junction, and there will be some electrons field on the left and some on the right. There's a difference of chemical potentials. And there will be no statistics for electron transfers in this interval. Why? Because electrons on the left cannot find a place on the right, and vice versa. So everything happens only in this window. Nothing happens also at larger energies, but it's natural because there are no electrons at larger energies. So everything happens within a rather narrow of energy strip of the order of voltage or temperature. Okay, by that time, it has been derived in the beginning of 80s. That's been a masterpiece of theoretical physics. The authors should have been proud of deriving this formula. It was perhaps disappointing for them that the result you can explain to any street hooligan. Let me switch to the language of street hooligans just for a change and tell what's going on. That nanostructure, we take one channel for simplicity, is just as a gambling machine. And electrons, which wanna transport, form a very dense queue without any interruptions. Now they come to this gambling machine, they win with a chance T. They win with a chance T, they transfer. Otherwise they are reflected. Right, so there is no noise in this queue, but there is a noise in transmission. Some empty places, random empty places in this queue. Right, if the winning chance is 1, the queue remains dense. Also, here, there is no noise as we expected. If transmission chance is small, then the events are independent. So everything is in place. Rather simple answer, which can be explained to anybody who understands a little bit of gambling. Right, that was counting statistics for electrons. Let me talk about perhaps philosophical concept, but very useful to understand quantum transport. Let me start with a simple fact. We are all persons, we are all individuals, and we are different. But if we come to ATM machine to get our money at the wall, the machine cares only about our card or only about our PIN code. It doesn't matter what's the color of our eyes, what are our political conventions. ATM machine would do the same for you. Only the code matters. A little bit the same is with quantum transport, quantum contact nanostructure. It could have very many details. It could have design peculiarities, impurities, imperfections, complex gating systems. Quantum transport cares only about a set of transmission coefficients, right? So all details should go to this set, right? Another piece of information. If you really try to make nanostructures at this level of technology, it is actually impossible to make identical ones. Suppose we want to do something simple, we want to make diffusive conductor without tunnel barriers, without ballistic point contacts, with a certain resistance, for instance, 50 ohms. Okay, we do this, and that's what we get. We have individual spectra of transmission coefficients. So each black line in this figure is the value of transmission coefficient. All right, we see many of them, which means that conductance is high. And indeed, did I say 50 ohms? Yeah, it's something like that. It is like 100 times more than conductance quantum. And the question arises how to characterize a type of quantum conductor rather than individuality, right? So you're all individualities, but you're all students. I'm individuality, but yeah, I'm still a teacher. And the proper quantity is to look at is transmission distribution. So suppose we did many nanostructures of the same kind, and we estimate a probability for certain density of transmission coefficients in an interval, right? Fine. It's, by the way, this pink curve I put into these plots. Oh, you see that there's a very dense distribution here, rather dense distribution here, and something in between for intermediate transmissions. So that pink curve, well, I have a formula for this, for diffusion conductor, characterizes the type of the quantum conductor, its design, if you wish. All right, and let me finish the first lecture just showing you, illustrating the statement with two more examples. So quantum contact is individuality, type is a transmission distribution. Here I took an example of tunnel junctions, right? So you see that all transmission eigenvalues are closer to 1. They are concentrated, close to 0. They're concentrated here. Or I could take a realistic QPC, and all transmission coefficients concentrate here. In a couple of lectures, we will be able to derive actually these formulas for transmission distribution, if you're interested. Okay, that was lecture number 1. Let me switch to lecture number 2. Let's see. Oh, other questions, sorry. What did we learn? We learned quite many things. That was last piece about counting statistics. but mostly we talk about scattering approach. We talk about Landauer formula. We talk about scattering of electronic waves, right? And we spent some time trying to kind of get used to this strange concept that any nanostructure can be accurately described by waveguides and a set of transmission coefficients barriers for each transmission mode in the waveguide. All right, that was short summary. Let me get the lecture to here. I get this one. So today we talk about the quantum interference. I would be happy to jump immediately to quantum interference, but I will be able to do so only after some stuff which might be boring, but which is an extension of scattering theory we have to do to look at interference in quantum transport. We will look first at multi-terminal nanostructures. It has more than 2 leads. We will formulate scattering matrix and Landauer formula in this approach. And all that, basically, I need to talk about beam splitter in the context of quantum transport. And after that, I'll get busy with interference. Good, so let us try to get through this multi-terminal stuff rather quickly. It is not very exciting anyhow. So what I have here is a sketch of 3-terminal nanostructure. There are 3 leads which I can bias independently at different voltages. V1, 2, 3. All right, what do I have to measure are currents. So in each lead, I can measure corresponding current, which of course depend in principle on all voltages I apply to nanostructure. Right, so the goal of quantum transport calculation, or the goal of measurement, is to express these currents, 3, in terms of 3 voltages. Good, so what else I would like to mention? It is very common to tune nanostructure with gate electrodes, which I picture like this. I put capacitances here to stress that there is no electric contact between nanostructure and these electrodes. Electrons do not jump through capacitors. But, well, if you change the gate, you can influence your nanostructure. We will see many examples of this influence. Fine. Let me talk about scattering matrix, and the concept of scattering matrix is essentially the same, with only detail. Now I want to mark from which lead, from which terminal the electrons are coming and where do they go. So as such, scattering matrix will have double indices. Right? For instance, what does this mean? I have a terminal alpha, and there are several channels in this terminal. So I have to say in which channel does electron come. All right, and it goes to another terminal, terminal beta, to channel number M in this terminal. Fine, so the difference between what we know, that there are more terminals, it's not only left and right, there are more possibilities, right? And since current is measured in a terminal, not in a channel, but in the whole terminal, we have to mark channels according to their terminals. Fine. Properties are essentially the same that we have. Very important property is unitarity, which, as we learned, just manifests the fact that electrons conserve at the nanostructure. They don't appear here, they don't disappear, the structure. The number of electrons which you send is precisely the number of electrons which go out. Right? Unitarity, I just rewrite it in these terms of double indices. Look, concentrate for a second if you can follow. So it's matrix multiplication and just expressed in terms of indices. You sum up over indices of terminals and transport channels in each terminal. Good. We also mentioned symmetry with respect to time reversal. And I rewrite this from a little bit different now, right? So usual way to break time reversibility is to set magnetic field. So if you go to time reversal situation, you have to change the sign of magnetic field. So time reversibility relates scattering matrix at plus magnetic field and scattering matrix at minus magnetic field. And what is the difference that we already discussed? Is the difference is the order of indices. We look at electron which goes from my left to my right. If we change the direction of motion, it goes from right to the left, from the right to the left, and right. It's a permutation of indices. Fine. Those are properties of the scattering matrix, but let me understand what we are up to, what is to compute to characterize these currents. Okay, let's suppose that we apply sufficiently small voltages, we are near Fermi energy, and let us assume that there is linear relation between currents and voltages. I just want to stress that this is a matrix relation, yeah? So for this three terminal structure, there are three voltages forming a vector, three currents forming a vector, right? So there's a three conduction matrix. We usually don't talk much about this at electronic engineering, but it is a fact. There are some obvious properties for this conduction matrix, and that hold for any matrix for any situation. It's based on very fundamental concepts. First of all, it's current conservation. Electrons do not arise at nanostructure, and that means that whatever circumstances, the sum of all currents from nanostructure is zero. That should happen at any voltages, and that means that summation of this matrix, conductance matrix, over first index should give zero, always. Another property, very symmetric property, if you rise all voltages with the same amount. We rise voltages, but we don't provide any voltage differences. We don't provide a slope for the current to flow, which means that there are no currents, whatever voltage I applied. Good, that means that if you sum it up over second index, you also get zero. That explains why we don't use any matrix for two-terminal conductor, right? Because in principle, it's 2x2 matrix, as I put it here. But owing to these properties, it has only one independent element, conductance. So it doesn't make any sense to present it as a matrix. All right, everybody understands this formula, everybody recalls how to multiply matrix and vector. Or shall I? I could. All right, good. Then we can switch to Lambda formula. What I put here is similar to Lambda formula for two-lead conductor. There's a current, and the current is contributed by electrons at all energies, and filling factors come into play. All right, as you see, there are two large terms, and the first term is very evident. Look here. It describes transmission of electrons from which start in terminal beta, right? So it comes with corresponding filling factor, and that go to terminal alpha to produce current there. All right. So what's the coefficient here? It's a probability of transmission chance to start in terminal alpha and to go to, from beta to alpha, but yeah, usually this matrix is symmetric, so there's no problem with this. Right. What is the second term? Second term it depends on filling factor in the same terminal. As such, it should tell you something about reflection, right? So so some electrons come in to terminal alpha, part of that are reflected, and that gives you some current in terminal alpha. Number of coming and reflected particles in terminal alpha is not the same, that is balance. Okay, but how to compute coefficient here? Well, it is just the sum of all probabilities not to go to terminal alpha. Yeah, because sum of the probabilities is 1, so one can compute it. This. Very good. We could easily run 2 fast foolproof checks. We know that this expression should satisfy current conservation, which means that the sum over alpha must be what? Yes, must be 0. So how we can achieve this? Well, if we just add sum over alpha, one can, let me do it like this. One can exchange alpha and beta under the sum sign. I do it here, that becomes beta. Well, these 2 terms cancel. Fine. If you do it for current in equilibrium, all these filling factors are the same. And again, then it cancels for each terminal. Good. Probability of transmission is expressed through scattering matrix. Basically, it's just the sum of individual transmission probabilities from each channel in terminal beta to all channels in terminal alpha. Fine. That's how to compute conductance matrix. Basically, it's just expressed in terms of these probabilities. Nothing very important. Right. Time reversal symmetry. It follows from this property of scattering matrix, but I should say it also follows in general context. Again, if there's no magnetic field, if time reversibility holds, the matrix of conductances is symmetric. If there is magnetic field, there is anti-symmetric part, which is proportional to this magnetic field. You might know about Hall effect. This is it's anti-symmetric conductance proportional to magnetic field. Those are general relations not restricted to electrons. It's what Professor Zager once derived just from thermodynamics. Good, so we are done with Landauer formula. Let me get to the subject to the very simple element which I need to go to interference in quantum transport. It is called beam splitter, and basically it is taken from optics. Right? In optics, they split light beams with this. One can also split the electrons. We look at the simplest beam splitter with only 3 channels, 1 channel in each terminal. I could write here an arbitrary 3 by 3 scattering matrix, but I choose a simple example, which is also practical. Opticians frequently use such a beam splitter. And that is reflection is 1, with respect to channel 3. First, let me put it into words. If you send a wave in channel 3, it is not reflected at all, and it goes in equal proportions to channel 1 and channel 2. Good. How we can see it in numbers of scattering matrix. Okay, it comes in channel 3, so we need to look at this row. And if I square it, I get the probabilities to go to channel 1, channel 2, and there's a 0 probability to be in channel 3, so that to get back. Right. It would be very handy, very convenient to have a beam splitter which has this property for every end. Very symmetric one. But eventually such beam splitters are forbidden. One cannot find such a unitary matrix that it is reflectionless from all 3 terminals. Good, that's why when we come from terminal 1, we see a bit different situation. Let's look at it, let's look at this row. So again, I want to square these amplitudes to get probabilities. 25% chance for reflection, 25% to go to channel 2, and 50% to go to channel 3. All right, that's the scattering matrix, that's the probabilities associated with the scattering matrix. All right, I guess I just want to show the conductance matrix for this beam splitter. Again, it is computed from the matrix of probabilities to go from one channel to another, and it should satisfy the properties. So let's check it. Sum of these 3 must be 0. Sum of these 3 must be 0 as well. Okay, that's satisfied as far as I'm concerned. Fine. That's a simple example. Equal voltages here. So there's a maximum current which you can have in one channel. It goes to terminal 3. And okay, it's a bit logical that currents here are the same. Fine, let us see. Now I want to switch the topic, and perhaps it's a convenient time for a break. Let's don't make it long. Let's have 6 minutes break, if you don't mind. Oh. Recording, sir, second part of the lecture, switch of the topics, and I want to tell you about the greatest experiment of all physics, also all natural sciences, at least that shows up in most of enquêtes this point. It's a common opinion, right? So what experiment I'm talking about double slit experiment. There are 2 slits, 1 and 2, and there are waves. There must be waves, otherwise it doesn't work, which go from point A to point B. Can be any waves, can be light, can be pressure waves, sound waves, can be electronic waves, right? And what makes the trick? Let us compute probability to go from A to B or for light waves, for instance, intensity at point B having a source of light at point A, right? It is basic principle that we have to add amplitudes A1 and A2 and square it to find the probability. All right, let us look at this algebra in more detail. It is a sum of two squares, which are accurately probabilities to go either through first split or through the second slit, right? So if we think of classical particles, that has to be it. The total probability is just the sum of the two. In fact, wave mechanics dictates that there is a third term, interference term, which depends on mutual phase shifts of these two amplitudes. Right, this is quantum effect. If you think of particles, it means the important thing. One cannot say that particle has taken either slit 1 or slit 2. Somehow it took them simultaneously. It cannot be localized in slit 1 or 2. So that's a remarkable effect which stresses the difference between particles and waves, or whatever, between classical and quantum. Right. And we are going to talk about manifestations of interference in quantum transport. Let me start first with phase shifts, right? So for interference, we have to look at the phase shifts. Let us see where and how we can accumulate phase shifts for moving electrons. Let me make some simple calculations. Let me assume an electron, one-dimensional electron, which moves in some smooth potential, so there is no reflection. Very well, then its wave function is just a phase factor, like this. And what determines this phase factor? The local derivative of this phase is just a local value of wave vector. Okay? Usually for plane wave, it doesn't depend on x, but it could if there's potential. Well, how to figure out what is this k vector? All right, it's just energy conservation. So k vector comes from kinetic energy. I hope you remember that. This is kinetic energy. There's also potential energy. Total energy is the same. So we have kx, which depends on x. All right, this is just a phase shift. It is instructive to look at energy dependence of this phase shift. It will tell you something, but we can just do it with our hands. We need to differentiate this phase with respect to energy. So basically we need to differentiate this guy with respect to energy. And what we get, it's inverse velocity. So we integrate over inverse velocity. What we got? We got propagation time. So fun enough, one would not intuitively think that the phase cares about time so much, but it does. adjusted information about propagation time is encoded in energy dependence of the phase. Right. So now let me talk about voltage dependence. Let me imagine that I have some gate voltage, no direct electric contact, but still some influence on electrons in the structure. So that's extra potential energy. I can differentiate, put it here, differentiate. This is what I get. So the phase which is accumulated is proportional to this extra gate voltage times time, which is natural. More time it spends checking this gate voltage, more phase it will require. Let me state, and it looks rather obvious statement at the moment, that the phases accumulated by motion in opposite directions are precisely the same for this mechanism, for this potential energy mechanism. Very good. And okay, it's all clear. It's all crystal clear. And perhaps I could ask you what was the most, let me formulate like this, what was the least comprehensive part of your physics course? What was your opinion? What was your impression? What was most difficult to comprehend? Didn't you have any difficulty whatsoever? For me, the most illogical part, most difficult part of physics course is to understand the names of physical phenomena. And that's also the case. I still don't understand. Perhaps you understand it better. Then please explain me why this phase shift is called dynamical phase. But it is called so. All right, so we need to memorize dynamical phase. It's a phase which doesn't depend on the direction of motion. There is another source of phase shifts which comes from magnetic field. I need to recall something which remind you something which you perhaps don't know, although you should. Let's see how much was it left from your basic courses. Well, first of all, there's a trajectory I got and I would compute the full phase shift along this trajectory by doing the following. I just take again a local wave vector. I call it momentum, divided by h bar, not to forget. And then the full phase is just sum of these elements. What's important here is a inner product. Direction of momentum, direction of trajectory. And then I recall a formula from basic physics. This is how charged particles interact with magnetic field. It involves vector potential of magnetic field, and this is an extension of momentum of a particle. All right, let me check if you know what we're talking about. Who knows what is the vector potential of magnetic field? That's great. Okay, who knows that it extends momentum as it's written? Ah, that's good. Eventually, I didn't know when I was a student. Well, when I was a bachelor, I learned it in master program. Fine, good. So how we can use it now? Well, we just put this addition of from magnetic field over here, and we get the formula for the phase shift. So we have to follow the trajectory and take in a product for each value of vector potential. Right? It's a contour integral. We will note that, well, it's also obvious it's magnetic field, so time reversibility is broken. The phases accumulated for opposite directions are precisely opposite. Fine, so it's a distinct phase, distinct way to get phase shifts. And again, in comprehensive notations, you would be surprised, or perhaps you know, but this is called geometric phase. Dynamical phase we have, and geometric phase.
One question, is it known as well as Berry phase? Is it the same one?
No. Berry phase is something related to adiabatic change of wave function when you move in some parametric space. That can be also a space of in band structure. When electrons change their momentum, they move in band structure. They can feel Berry curvature, but it's not the case. It is just geometric phase. There are also manifestations of Berry curvature in quantum transport, but they're less pronounced, but I don't talk about that. Right, so phase shifts in magnetic field. And now I want to mention very strange suggestion, which which kind of immediately follows from quantum mechanics, but it took like 30 years before people could really believe into that. Rather strange, a counterintuitive experiment. All right, first of all, it is the same double slit experiment in magnetic field. Good. So there are electrons which come to these two slits and they take either path 1 or path 2, and we kind of catch them at this point. So how we can compute phase shift, which enters interference effect? It's a difference of phases accumulated at this path and at this path. Since directions are opposite, the difference together, well, it just corresponds to circulation. For circulating trajectory, it's all in the same direction. Good, so we have a contour integral over vector potential over a trajectory. Then I don't know, yeah. So far I got positive answers from you. So how about Stokes theorem? All of you. Stokes theorem. Okay, good. Stokes theorem. It tells you something about contour integrals and surface integrals. For this particular case, it's expressed as contour integral in terms of surface integral from magnetic field. And that amounts to full magnetic flux through this area. All right, one can say, so what? So here I rewrite it in convenient units, introducing flux quantum, something which is made from fundamental units like conductance quantum. We have already studied. What is the catch? The catch is, it's kind of, that's why people did not believe into this effect for a while. The catch is that the electrons are influenced by magnetic field in the absence of magnetic field. Right? To make it kind of practical, let's imagine that we have a magnetic coil in this area. There's some flux in magnetic coil, but we know that if a coil is long enough, there is no magnetic field outside the coil. So there is no magnetic field at these electronic trajectories. And for a kind of pre-quantum physicist, that would mean that magnetic field doesn't have any influence on these electrons. Nevertheless, quantum electrons do feel magnetic field. Although they never go to the coil, they don't have a chance to check whether magnetic field is there. They actually feel that vector potential of magnetic field, which is not zero if magnetic field is zero. Right. I wanna get one thing from the Aronoff-Bohm effect. We are talking about the phase, and all this is periodic. The result of interference is periodic in this phase, right? That's why the result will be periodic in flux. If you measure something as a function of magnetic field, interference would result in periodicity in flux. Good. I got a very important topic, perhaps the most important one in interference and quantum transport. I want to talk about double junction. What do? I took two very simple conductors, one-channel conductors. We have got an example of scattering matrix with certain transmission coefficients. And I would like to understand what will be transmission coefficient of the whole structure if I just put them in series. It's a simple thing, but if you look at it, it might come very surprising. There is no answer. There is no answer because we miss something. In that case, Russian-speaking people have a kind of advantage in understanding the situation. Because in Russian language culture, there's a very stupid riddle for children which explains what is going on. Let me try it on you, perhaps you would also comprehend it better. The riddle is like this. A and B, think of these two contacts, let's call it A and B, have been sitting on a roof. A has fallen down. B has fallen down. What is there on the roof?
Nothing.
Let me repeat it again. A and B have been sitting on the roof. A has fallen down, B has fallen down. What is there on the roof? And that's precisely what we are missing in our setup. When we connect two objects, there's something which provides this connection. So and is not nothing. And this and, in our case, is characterized by a phase shift. One can go from A to B, accumulating certain phase shift. And that appears to be important. Let me calculate, and that will be perhaps at the moment tedious calculation, but let me still do this. Let me calculate the full transmission amplitude of going through these two junctions. I have to sum up terms which I drew by these diagrams. What does it mean? I consider all possible processes of propagation. They differ by number of reflections from the backside of the contacts, or in other terms, a number of round trips between the contacts. What is the simplest situation? No round trips, however. Transmission through these contacts. What is the amplitude? All right, I just have to multiply partial amplitudes left. I take into account this phase factor, right. Okay, now I want to do it with a one bounce. To left, phase factor, no, a reflection. I accumulate the same phase factor again, it's dynamical phase. Left reflection. Once again, I go through the end, through the region connecting A and B to scatterers. And finally, I get out. Right, I could do more rounding trips, and I understand they all that differ by this factor. So it is a geometric series with this factor. Now I could apply my math skills. I know how to sum geometric series, so let me write it down explicitly. 1 plus x squared plus, well, you understand the logics, is, tell me.
1 minus x.
Yep, 1 minus x.
If the absolute value of x is smaller than 1.
For our purposes, it's indeed smaller. It is guaranteed by the fact that all reflection amplitudes are smaller than 1 in modulus. Good, that's what we have. So it's a quantum way. We add amplitudes. Classically, what we would have to do, we would have to add probabilities for each process. Well, one can also compute them. So one just take each term, square it, and sum up probabilities. Fine. So that's the answer. I just square it. And let us see what we have. So one can express it in terms of transmission coefficients of the left and right, but there is this unknown parameter, and there is a phase shift characterizing the link between two junctions. It is there. Funny enough, if I average over this phase shift, just taken to grow formula, I would suppress all interference effects thereby. Interference is always something which oscillates, right? So if I integrate, I kill all oscillating terms. Good. This is pretty much classical result obtained after such integration. As if there were no waves, but particles. Let me look at these plots. It's very instructive. So what I did here, I plotted first this transmission coefficient versus phase. And now I recall that phase eventually energy dependent, right? So I could plot it also versus energy. And what I see is something periodic, and that has peak structure. If all transmissions are big, and for this example, those are the same, it's symmetric, there are some interference, some oscillations, but basically all transmissions are big. Funny thing happen if transmissions are very small. Then you kind of expect that it doesn't transmit whatsoever. That's not entirely true. As we see in this plot, the transmission can be almost ideal, the transmission through the whole structure, at certain resonant energies. All right. If I'm in larger audience, I usually ask at this place if there are patriots of French Republic in the class. I expect you're not, but still, right, it must be two French names which should come in immediate association with this. You know that, you have heard that, I'm pretty sure, so let me tell. That's Messieurs Fabry and Perron. You understand that in the concept of optics, what you do, you put two semi-transparent mirrors, right? And there's some interference resonances between those. But okay, light is a wave, electrons are waves. So we see Fabry-Perot resonances here as well. Even for very small transmissions, there is a distant peak. All right, we will study it in detail. We will show that indeed it's a very fundamental property of quantum transport having these peaks. Good, that was double junction. Since we still have an exam, and for exams there will be some problems to solve, let me tell a little bit about formalities, about calculations. Over here, right, what I want to say, we have got this answer by summing up these partial trajectories. It was rather easy for this concrete structure. For more complex structures, it could be difficult, right? Because you have to get good bookkeeping of all trajectories. Fortunately, this bookkeeping can be done automatically if we understand how to make a system of equations for partial amplitudes in this wave. All right, so let me treat the same system a little bit differently. We still have these two scatterers. Each is characterized by a scattering matrix. Let us see which equations can we make with these scattering matrices. Left one. All right, so it connects incoming amplitudes and outgoing amplitudes. Let us name the something. Well, we look at the wave which comes from here. So this is reflection amplitude. And after it passes, there are yet unknown amplitudes alpha A and B. Okay, so we look at incoming 1 and B, and they're related to outgoing amplitudes. One equation. Same we do for the right. And now we need to relate C and B and A and D. One could also say there's a scattering matrix over here, but very simple one, diagonal one. It just multiplies them with a phase shift. Okay, we are done. We have a system of linear equations, and if we solve it, we eventually get this amplitude we are interested in. So there is a more practical way. In this case, you don't have to think about all possible trajectories, don't have to keep them, but rather you write one system of equations and solve them. Now I can come to description of Aronoff-Bohm effect in quantum transport. So that's a simple setup I could imagine. And you understand now why did I need these beam splitters. If I just took two scatterers, these passes would have been completely equivalent. And I could not put magnetic field between these passes. With beam splitters, you can. So I did put it. So let me look at phase shifts, which are accumulated, for instance, above. I see they are different. And I kind of separated dynamical phase, chi1, and geometric phase, phi1. The sum of two geometric phases, it's a flux in proper units. One cannot live without. Good, so beam splitters, and one wants to compute transmission coefficient as a function of flux. I do not want to sum up all possible trajectories. It would be too much. But I find it instructive to look at certain trajectories, simple trajectories. So I don't want to sum them all, but I would like to understand the interference of simple pairs of trajectories. That's what I draw. Trajectories A and B are very simple, simplest ones. So electron just either takes upper path or lower path. Two ways, two slits, which can interfere. Fine. The rest of trajectories are a bit more complex. What is important for me, what appears to be important, so the complex, they involve one reflection, right? That there are pairs of trajectories. Let us see which one. Yeah, for instance, C and D. And electron does almost same trajectory, except a loop over here. And this loop, if I only took, let me just check to be sure. All right, it's D and E. Yes, sorry. D and E. So these two trajectories just differ in direction of circulation of this loop, either clockwise or anti-clockwise. Good. So basically, I won't look at interference of all the pairs. I would look at the interference of A and B and D and E. Right. Interference example 1. Fine. I want to sum up all these phases along each path. I want to take the difference between these phases. Interference always checks the difference of phase factors on two possible paths. Well, they accumulate dynamical phase, they accumulate geometric phase, so that's what I got. It is periodic in flux with a period of 2 phi naught. And it depends on dynamical phase. All right, that's great. But remember that if we average over the phase, the oscillations are suppressed. They are gone. So it's supposed to vanish if we average over dynamical phase. Oh, one could say this is a common property, but wait a second. Let us look at the interference of these two trajectories. And if you look at it, you make sure that dynamical phases for these two trajectories are precisely the same. You take difference with no dynamical phase, so the phase difference only involves magnetic field, magnetic flux. There's also additional loop they make, which means that this is bigger than we had before, and the answer eventually phi naught periodic. And it does not vanish if one averages over dynamical phase. Fine. Right, here I just sketch all equations which you need to solve to get the answer straight. Okay, for this case, it's too complex to count all trajectories, but with equation method, one could deal with this. Again, there are equations which are from beam splitters. There are equations from these places, upper arm and lower arm. And with that, one can solve this. That's the answer for symmetric case. I just plotted it versus magnetic field versus the flux. And black lines are at certain values of dynamic phase, and they just periodic with a period of 2π, while the result of averaging of a dynamical phase has a different period. It's very counterintuitive. If you average the functions with the period A, you expect the result to be periodic with the same period. It's not what's happening here. It has a different period. Right? We explained why. It's because of these finite trajectories. Good. All that looks rather abstract, but fun is that with this, we can explain some pioneering experiments in quantum transport. First experiments which have proven that electrons in electronic surfaces are eventually waves. Okay. I must perhaps mention some political background. That was been made in 80s, and perhaps your grandfathers, grandmoms told you that that was quite stressed political circumstances. There was a competition between almost two symmetrical systems, Soviet Union and United States. No, you know that not every competition is bad. So because of this competition, there were quite interesting scientific activities on both sides. They've been competing. Good. So this is Soviet quantum interference. The technology was not at American level, but they've been very inventive. So what they wanted to do is a small cylinder, which could be long, but with very small cross section, with very small opening. They use a property that some crystals eventually grow as whiskers. They really make very thin and long stub. Like this. So it's perhaps hundreds of nanometers thick and could be 1 millimeter long. Right? And they just evaporated conducting material onto this whisker. Right? So that was a rather long cylinder, but with very small, with a reasonably small cross section. Good. So they applied magnetic field in this direction, and they measure the resistance. Very simple electric measurement. What did they find? As you see, there's some linear dependence on magnetic field implied. Well, that one can readily believe. Everything depends on everything, so linear dependence is not really unexpected or interesting. But there was oscillating dependence, and it's not of a very big scale, imposed on this. Right. So let me get some transparencies back. For instance, this one. And it's kind of contour question, if you wish. Which period did they see? Long one or short one? I need to remind you that these were lonely period was for individual trajectories, and the 30 period was for a result averaged over many dynamical phases.
Short one.
Yes, how do you motivate this?
Well, they're measuring it through the length of the tube, so there's many.
Yeah, you're right, sir. Since the tube is big, there are very many ways, many trajectories to go from one end to another end. And they have very distinct dynamic phase. But there are pairs of these trajectories where dynamic phase cancels, and that's what they saw. Good. But all right, as I said, there's been competition, sir, in several years. Americans did alternative to this. All right, sir, if you look at this side, you might also see a cylinder, but that was with a very small dimension perpendicular to the plane. So there was a small loop in a metallic film. How did they do that? That kind of made a mask of this shape and evaporated a thin metallic film. Into this, they needed contacts, but the loop was essential. What did they see? They see something which they called grass. Something which oscillates, but in a rather random fashion. There were no regular oscillations like we have seen in previous experiment. Nevertheless, they will be able to make a spectrum of these oscillations. You know how to make spectrum. You have the data set, you make Fourier transform, right? And that Fourier transform has shown some peaks, which indicated the period. Okay, I put it here already. It's a larger period. So in this way, they can see trajectories with individual dynamical phases. Several ones. That's why it's been noisy, because it's been contributed by several trajectories with shifted dynamical phases. Right, but yeah, if you look at the spectrum, you can see these periods. Fine. So one can say there are two types of interference in magnetic field. They are affected, in fact, have different origin, and both effects have been observed by that time. Right, that was about interference in quantum transport. Any questions about the total lecture? We still have a minute. So just to remind, we have started with multi-terminal things. We have formulated scattering matrix for multi-terminals. Was a bit boring, but well, at least we know how to describe complex circuits. Right, Landau formula, and all that was to talk about this simple beam splitter. Right, then we talk about interference in general, two classical contributions, quantum contribution. About the nature of phase shifts, magics of Aronoff-Bohm effect. Then we get to quantum transport. We understood interference without magnetic field first. We understood the importance of and in general. I hope you will remember this riddle and tell your children. Right, double junction. And finally, we talk about the Aronoff-Bohm effect and even touched couple of experiments. Good. Thank you for your attention.